Hello, you're welcome back. All right, so now let's now get to the application of Laplace transform. Very important application, okay? That is the solution of ordinary differential equation by Laplace transform. Okay, so all the Laplace transform methods that we've learned, okay, up to the inverse Laplace transform, we are going to apply it in the solution of ordinary differential equation. Let's look at the steps. First of all, we have to convert that equation, the differential equation, into its Laplace transform. That's number one step. Then, of course, you insert the initial value, all right, that is given for that particular equation. Then make the dependent variable, which of course is in most cases x. We have s is equal to f of t. So the dependent variable is x. S is equal to f of t. We're going to get to that. So we make that uh, dependent, we make the Laplace transform, please pardon me. Okay. Okay, so let me, from here. So the next step is to make the Laplace transform, the Laplace transform of the dependent variable, because your answer, the answer of an ordinary differential equation is always written in terms of it's always written in terms of y. Okay, this the dependent variable being a function of the independent variable. Okay, all right. So what you're going to do is we'll make the Laplace transform of the dependent variable the subject of the expression. Okay, so now for us to now finalize the equation, we have to find the inverse. Find the inverse Laplace transform of both sides. Inverse Laplace transform of both sides of the equation. All right. Now, of course, this method we are going to apply it. Okay. But first of all, let's look at the notations we use in Laplace transform. All right. Anytime, of course, you know that x, first of all, the function is a function of t. S is equal to f of t. That is the function. All right. F is a function of f of is a function of t. F of t. S is equal to f of t. So anytime you see me using f dot x dot, please pardon me, it simply means that we am talking about the first derivative of f, that is f prime t. If I'm using x double dot, that is the second derivative, f double prime t. Okay, so on and so forth. Triple dot means the third derivative. All right. Now, if I use x1, it simply means that I'm looking at the first derivative of the function, okay, when we actually substitute the initial value of t, all right, into the function. Okay, so call that fx1. x2, the second derivative when we substitute the initial value. So please take note of that. All right. So we proceed. Okay, so now let's look at the Laplace transform, because the very first step is we're going to, all this notation, we're going to convert them into their different Laplace transform. Both the derivative and, of course, the expression for the function, all right, x being equal to function of t, we are going to transform them into the Laplace transform. Let's start with x, okay, the dependent variable x. The Laplace transform of x, which of course x is equal to f of t, is x bar. So that is the notation. So anytime you see me using x bar, that is the Laplace transform of that dependent variable x. All right. Then x Laplace transform of the first derivative, that is x dot, is given as x x bar minus f of 0, or of course f of 0 is x 0. Okay, like did I include that, or I didn't include that? So invariably, that's one I didn't include here. Let me actually fix it in. So if you see me using x 0, that means that's gonna be f not prime, just f of 0. Okay, x 0 is just f of 0. So please take note of that. So the Laplace transform of the first derivative is given as x bar minus x 0. All right. Now the Laplace transform of the second derivative is s square x bar. Now that's what I want. That's something I want us to establish, is the relationship. Look at what is happening here. Okay. Now the Laplace transform of the derivative, okay, of derivative of the dependent variable. If you look at how the relationship or the pattern that is being established, okay, we start with the highest power of x, this x right here, which of course s power 1, that shows that's the first derivative. Okay, then x is actually reducing in power. X reduces in power while the derivative, okay, x is reducing in power starting from the highest, okay, while the derivative is actually increasing in power from starting from f of 0 to f prime of 0, f prime of 0. Okay, so let's look at that pattern so that it will actually make sense. Now, this is the Laplace transform of the first derivative, that is x bar minus x 0. Now, for the second derivative, I have s square, okay, then x bar, then this x reduces to x raised power 1, okay, then of course I will start, once we get to, then the very first, I have to start with f of 0, and then the x in this case now reduces to x raised power 0. Of course, x raised to power 0 is 1, while f of 0 increases by 1 prime. Okay, so it actually stopped there. Okay, we actually stop the very moment this x here actually reduces to 1. Okay, so let's look at that of x triple dot. So that's going to be s cube x bar. So now s cube x bar actually reduces to s square. Then I now I start with f of 0. Okay, then of course from s square, the s square actually reduces to x raised power 1. Then of course this increases to f prime 0. Then of course I'll go again from x raised power 1 to x raised power 0, which of course is the last. Then this also increase from to f double prime 0. Okay, f double prime 0. Let me write that. Okay, that it wasn't clear. Let me clean it up. So once you know the pattern that is established, it's easy for you to write that transform. Okay, so this is Laplace transform of the third derivative. So we're going to start with s cube x bar. Now the s cube reduces to s square. Then I now start with my f of 0. Okay, then the s square reduces to x. Then this now increases to f prime of 0, as you can see. Then from here now the s raised power 1 reduces to s raised to power 0, okay, which is 1. Then this now increases to f double prime of 0. So please just take your time and look at the pattern that is developed. That way you will be able to remember it. Okay, so now let's solve a very simple equation. Okay, so this equation, the initial value is actually given. Okay, let me get from where it is. Okay, so initial value of t equal to 0, s is equal to 1. Okay, the initial value is given as solve this at the initial value equal to 0. Okay, x is equal to 1, and of course x is equal to 1 and x 0. X 0, okay, is equal to, is equal to 1. So solution. Okay, so let's, the very first step, we have to convert this into the Laplace transform. So this is the xdt, which is this is the same. This can be written as x dot minus 2x equal to 4. Okay, so let's convert this. S dot, you know what it is in Laplace transform. That's going to be x bar. All right. Then of course x, to convert x, we still have what? X bar, 2x bar. Now to convert 4 into its Laplace transform, don't forget the Laplace transform of 4 of a constant is, that's 4 all over x. Oh, please, I made a mistake. It's not complete. The Laplace transform of x bar, okay, is x bar. Then of course the x reduces to 0. Okay, then and I have f of 0, which of course is x0. Okay, f of 0 is x0. Then minus 2x bar, then equal to the Laplace transform of 4, that is 4 all over x. Okay, so remember what we are going to, we are making the subjects. We have to make the Laplace transform of the dependent variable, which is x bar, the subject. So let me collect it together. Okay, so collecting that term together, I'm gonna have x bar as a common factor. Then inside the bracket I have x minus 2. So this, now I take it to the other side of the equation. That's gonna be 4 all over x. All right, then minus x0, and it happened that x0 is 1, so that is 4 all over x. Then of course this goes over, becomes plus 1. Okay, so now let's do this. This is going to be x bar x minus 2 is equal to, of course when you simplify this fraction, you're going to have x 4 plus x. All right, so the last step now, I have to make x bar the subject of the formula. X bar the subject of the formula. So what is the s bar? That's going to be 4 plus x, then divided by x into x minus 2. Okay, so now for us to actually complete our solution, so what we have to do is that we have to find the inverse Laplace transform of both sides of the equation, remember. Okay, so invariably I have to do the inverse Laplace transform of x bar. Then at the same time, I'm going to do the inverse Laplace transform of 4 plus x all over x into x minus 2. Okay, so of course, you know, for us to be able to do this, okay, so we have to express this into partial fraction. All right, so you know exactly how so I can simply use a cover-up rule. I can use cover-up rule to do that very fast. So using cover-up rule, so that simply means that my a is going to be equal to the limit of, I'll cover up this x, the limit of 4 plus x, okay, all over x minus 2 as x approaches 0. So if I put that, I'm going to have 4 all over minus 2, which of course is minus 2. Then for my b, That's going to be the limit of this time around. The limit of 4 plus x all over x as x approaches 2. As x approaches 2. So if I do that, I'm going to have 6. Of course, 4 plus 2, 6 all over 2, which is 3. So invariably, putting that together, okay, let me create a space. All right. Invariably putting that together, I'm going to now write this. Of course, the Laplace transform of x of x bar is the inverse Laplace transform of x bar is x. Okay, so I got to, let me write it down, x. Then the inverse Laplace transform of this, we've already done that, which of course is a. That is minus 2 all over, all right, minus 2 all over x, minus 2 all over x, then of course plus 4 plus x all over x minus 2, x minus 2. So we are looking at the inverse Laplace transform of this. Let me write it what the inverse Laplace transform of, okay, the inverse Laplace transform of a, which of course is minus 2 all over x, then plus b, which of course is 3 all over x minus 2. Okay, so let's take it one after the other. So s is going to be equal to the inverse Laplace transform of this. You know what it is? That's going to be minus 2. Okay, then plus the inverse Laplace transform of this. This is actually a coefficient. That's going to be 3. Then multiply by the inverse of this, which is exponent of 2t. Okay, so invariably that is my answer. So this differential equation is the solution is giving us x equal to minus 2 plus 3 exponent of 2t. Okay, so this is an example of how we actually use Laplace transform to solve differential equations. So we are going to look at more example in the next video. So see you in the next video. Thank you very much.